A lot of things happen between the drawing board and the end of the assembly line. And all along the way through the design, engineering, and production stages, one thing is in the minds of the builders: quality. For it's a quality product that keeps us in business. And there's one important factor that guarantees quality: precision. When it comes right down to it, precision is really a measure of the quality that goes into our automobiles. Here's a man who knows about precision and what it does for us. Hi, Rod. I see you and Dick are about set to talk about the precision that goes into the making of a car.
Right, Tech. In fact, we're going to talk about the ways that we, as master technicians, can maintain that precision in our own service shops. One of the most important things we can do is to read and pay attention to the clearances and tolerances that are specified for the various components of the car. And when a selective fit or a shrink fit is called for, check the dimensions very carefully to make sure the parts will provide that fit. To measure the dimensions, check clearances, and perform the all-around services that are expected of us as technicians, we need precision tools, and we need to understand their use and how to take care of them. So, let's take a look at some of the precision tools that are found in an automotive service department.
Sounds great, Rod. There's only one thing. The only tools I see here are micrometers, dial indicators, feeler gauges, and a torque wrench. Well, surely there are more precision tools around a shop than that.
There sure are, Dick. But these are the most common. Besides, a good coverage of these tools will take up about all the time we have for today. As a matter of fact, we better get started.
Right, Tech. Let's start off with micrometers. Micrometers provide the most precise measurements required for general automotive service work. With a little practice, you can take measurements as close as a 0.5 of an inch. A micrometer consists of a frame, anvil, spindle, sleeve, and thimble. Now, you'll be able to follow the explanation better if you remember these parts. Once more: frame, anvil, spindle, sleeve, and thimble. The measurements are taken between the anvil and the spindle. The anvil remains stationary, and the spindle is moved toward or away from the anvil by a precision ground screw inside the sleeve. The thimble is also attached to the screw, so turning the thimble opens or closes the space between the spindle and the anvil. One revolution of the thimble and screw moves the spindle 25/1000ths of an inch. So the graduation marks on the sleeve are 25/1000ths of an inch apart. Since the thimble and spindle move 25/1000ths per revolution, the barrel of the thimble is divided into 25 equal parts. Each one of these marks represents a spindle movement of 1/1000th of an inch.
I think I've got it now. One graduation on the sleeve is equal to the 25 graduations on the thimble, or one revolution of the thimble, right?
Right, Dick. And to make it easier to take a reading, every fourth mark on the sleeve is numbered. So the numbered marks are 100,000ths of an inch apart.
If it's any help to anyone, that 100,000ths of an inch is the same as 1/10th of an inch. Maybe you ought to give us a couple of sample readings, Rod, just to show how the two scales are added together.
All right, coming right up, Tech. In this case, the sleeve mark numbered 2 is visible, and the thimble scale is on 0. So the measurement is 200,000ths of an inch. Here's another example. This time the number 2 mark is visible, plus one of the unnumbered marks. So the measurement is 200,000ths plus 25,000ths, or 225,000ths. To go one step further, this example shows the same setting, except that the thimble is on the number 10 instead of on 0. Adding the 10,000ths to the 225, we get a measurement of 235,000ths.
Say, that looks pretty simple. Shouldn't be any trick at all to get an accurate measurement.
That's right, Dick. No trick at all, providing you set the mics right in the first place. How about it, Rod?
Right, Tech, and there's really no special trick to that. First of all, here's the correct way to hold a micrometer. Hook your little finger around the frame and turn the thimble with your thumb and forefinger. When you're turning the spindle down against the workpiece, keep the spindle and anvil square with the surfaces. If they're cocked, you can't get a correct measurement. And when you're measuring a round workpiece, be sure the center of the work is exactly between the spindle and the anvil.
Let me throw in a caution here. Be mighty careful how tight you turn that spindle down. If you don't have the spindle snug, you'll get an oversized reading. And if it's too tight, you'll not only get a wrong reading, but you could damage the mics too. Remember, it's a precision tool, not a C-clamp.
Right, Tech. In fact, some micrometers have a ratchet or friction drive on the end of the thimble. You can get the correct measuring pressure by turning the drive instead of the thimble. If you want to run the spindle down or up in a hurry, hold the frame in one hand and roll the thimble along your arm. Don't ever hold the thimble and spin the mics to change the setting. When you're not using the micrometer, keep a thin film of light machine oil on them and store them in a dry, dust-free place. I keep mine in the box they came in.
That's a good idea, Rod. And here's another one. Before you store a micrometer, whether it's in a box or just in a drawer, back the spindle away from the anvil 20 thousandths or so. If you don't, any metal expansion because of an increase in temperature will put a strain on the spindle threads.
As with any other precision tool, a micrometer should be checked occasionally. Use a master gauge to check the maximum and minimum points of measurement. In the case of a 1-inch mic, run the spindle down carefully onto the anvil and check for a 0 reading. Make sure the anvil and spindle are clean.
Hold it, Rod. What do you mean by 1-inch micrometer? I thought all mics had a 1-inch range.
They do, Dick, unless you use adapters. What Rod means is that the maximum measurement is 1 inch. Maybe you better explain that a little better, Rod.
Okay, Tech. Micrometers are available in different sizes and in 1-inch increments. A 1-inch mic measures from 0 to 1 inch. A 2-inch mic goes from 1 to 2, and so forth. There are adapters available to give the larger mics multiple ranges. For instance, there are adapters to fit the anvil of a 3-inch mic, which make it possible to measure any thickness between 0 and 3 inches, using the same micrometer. The same precision is possible for internal measurements, such as cylinder bores, by using inside micrometers. The basic principle is the same as outside mics, and they're read the same way. It might take a little more practice to get an accurate measurement with inside mics. It's easy to get them cocked in the bore and get an incorrect reading. So it's a good idea to take more than one reading just to check yourself. To get an accurate reading, make sure the mics are at a right angle to the center line of the bore. Then move them back and forth to find the maximum reading. By taking 2 readings, 90 degrees apart, you can determine whether a cylinder is out of round. You can also check for taper in the cylinder by taking readings at the top and the bottom. The difference in the 2 readings is the amount of taper. There's another tool for checking cylinder taper and roundness, but I think Tech has a short message for us right about here. Right, Tech?
I sure do, Rod. You can tell us about dial indicators as soon as someone turns the record.
Just about everyone at some time has to use a dial indicator to measure end play, backlash, or runout. And there are right and wrong ways to use even this simple tool. First of all, when you're mounting the indicator to take a reading, keep the support arms clamped as short as possible. This will help to prevent deflection. Be sure the anvil or finger of the indicator is at a right angle to the surface to be checked. Otherwise, you can't get an accurate reading. Always try to look straight down on the indicator dial when you're reading it. If you look at it from an angle, the pointer will appear to be at a different spot than where it actually is.
That error caused by reading at an angle is called parallax. Now, Rod, why don't you tell Dick about that easier method of checking cylinder runout and taper?
Yeah, Rod, I'm always interested in an easier way to do anything.
Well, there's a special dial indicator available that gives a direct reading of cylinder runout and taper. Basically, it's a standard indicator mounted on a special frame, which guarantees that the reading will always be across the true diameter of the bore. The frame has a pair of runners that contact the side of the bore to keep the gauge square. There's a handle on the gauge so you can check the bore at different points. To determine the amount of taper in the bore, hold the gauge at the bottom of the ring travel and turn the dial face until the 0 is under the pointer. Then move the gauge to the top of ring travel. The amount of pointer movement is the amount of taper in the bore. To measure out of round in the bore, merely insert the gauge and rotate it around the cylinder while watching for the maximum amount of pointer movement. You can also measure the diameter of the bore using this gauge. The contacts can be locked with a thumb screw and the gauge removed from the bore. Then simply measure across the contacts with a standard micrometer.
You'll find some tips in the reference book on taking care of your dial indicators. Now, Rod, how about covering some of the important points about feeler gauges?
Okay, Tech. Feeler gauges are made of a special hardened steel, ground to a high degree of accuracy and thickness. The thickness of each blade is etched in the blade for easy identification. The most common use for feeler gauges is to measure small gaps between two surfaces. The amount of feeler that will fit into the gap snugly is exactly the size of the gap. Feeler gauge stock is also used to fit pistons, especially after the cylinders have been bored and honed. A strip of the stock is attached to a spring scale to measure the piston fit. The piston is inserted into the cylinder upside down, with the feeler alongside the piston 90 degrees from the pinhole. Then the feeler is pulled out of the cylinder by pulling on the scale. Watch the scale to see how much force is required to pull the feeler out.
On Chrysler Corporation 273 and 318 engines, the amount of pull required to pull the feeler out should be between 5 and 10 pounds using a 1.5 thousandths feeler. Just make sure the piston and cylinder are clean and coated lightly with 10W oil.
Right, Tech, and if the pull is less than 5 pounds, you need a bigger piston. If the pull is over 10 pounds, the piston is too tight. Now let's look at a feeler gauge that should be familiar to you, but maybe you don't realize how important it is. Wire-type gauges are the only type to use for spark plug gaps and ignition breaker point openings. The flat feeler gauges are just not right for the job. Here's why. As you probably know, electricity will only work as hard as it has to in jumping a gap. In other words, the spark is going to jump across the narrowest part of the gap. If the two electrodes of a spark plug are not parallel, the spark will jump only between the points that are closest together. This will cause a weak spark and probably burn the electrodes pretty fast. On the other hand, if the electrodes are flat and parallel, there isn't any narrowest part, so the spark will cover all the area of the center electrode. That means a nice, fat, and healthy spark.
Well, that makes sense, all right, but what has that to do with the kind of gauge used to measure the gap?
You could probably figure that out yourself, Dick. But I'm sure Rod has a slick and smooth explanation for us.
Thanks, Tech. Yes, a flat feeler gauge will only tell you how much gap there is at the narrowest point. It won't tell you whether the surfaces are parallel. But if you use a wire-type gauge very carefully, you'll be able to feel whether the electrode surfaces are parallel. And if they're not parallel, you can even tell which side the narrow point is on.
Time is starting to run out, Rod. So if you're going to check us out on torque wrenches, now's a good time to start.
Before you start, Rod, I've been wondering why you included torque wrenches with the precision tools.
I was hoping you'd ask that, Dick. I'm afraid there are too many technicians who are inclined to take the torque wrench for granted. Actually, it's one of the most valuable tools you own. As you know, torque is the product of a force acting on a lever times the effective length of the lever. The effective length of a torque wrench is between the pivot in the handle and the drive square. In the case of specifications for tightening nuts and bolts, the torque specs refer to the resistance to turning offered by the nut or bolt. It's this resistance that is measured by a torque wrench.
I've been wondering about something. I've seen cases where two screws exactly the same size have different torque specs. How come?
Well, there are lots of reasons, Dick, such as the type of threads, bolt material, or the material they're threaded into. Here's an example. The torque spec for installing a particular spark plug in a cast iron cylinder head might be as high as 30 foot-pounds. The same plug installed in an aluminum head is tightened to 20 foot-pounds or even less.
Well, thanks, Tech. One of the very important reasons for using a torque wrench is to get uniform tightness. A good example of this is the cylinder head. If you don't follow the right sequence and tighten all the bolts accurately, you're almost sure to have a gasket leak. You especially need uniformity and accuracy in places where there isn't any gasket. For instance, the torque flight valve body depends on precision machine surfaces for sealing.
There are special attachments to handle those Phillips head screws on the valve body. As a matter of fact, Rod, I think Dick ought to know something about attachments, adapters, and extensions, don't you?
Right you are, Tech. An attachment is any work member that operates on the same center line as the drive square of the torque wrench. In fact, a plain socket is actually an attachment. An adapter is a work member that extends beyond the drive square. The most recent one I can think of is the adapter for tightening the head bolts on the Hemi engine. Extensions can be used to increase the range of a torque wrench. An extension that's the same length as the effective length of the torque wrench will double the range of the wrench. Just multiply the scale reading by 2.
Your reference book tells how to find the right scale reading for both adapters and extensions. Now, Rod, how about some tips on torque wrench care?
Okay, Tech, and there are some important things a technician ought to know about. On the open beam type torque wrench, as long as you can reset the pointer on the 0 mark, your torque wrench is probably accurate. If the pointer is bent away from the 0 mark, here's what to do. Simply bend the point back into place with pliers. The end of the pointer is quite soft and can be bent easily without fear of breaking it. But the shaft of the pointer is spring steel. So, if you have to bend the shaft, clamp it in a vise. If you try to bend it without clamping it, you might break the shaft loose from the head of the wrench. Check the pointer to see that it doesn't touch anything throughout its full travel. If it does, clamp the head end in a vise and carefully pry the pointer away from the point of contact. Don't ever stamp or etch letters or numbers into the beam of a torque wrench. That beam is precision ground to exact specifications, and any etching or stamping will weaken it, reducing the accuracy and shortening the service life of the tool.
I know there are a lot more things you'd like to talk about, Rod. However, the record is closing out, and I'd like to say a few words to all the master technicians. Rod has presented some mighty important information today. It's all repeated in the reference book for this session, along with some additional tips. Be sure to read it. And anytime you're working on a car, keep in mind that your service manual has a few pages of specifications in it. Read them and use them. If you do, you're bound to come up with that extra measure of quality.